his PhD at IHEP in Beijing on the development and case reconstruction of the reflector of the diabase central detector. I translated that from Chinese. I hope that's not too abysmal. He did his postdoc also at IHEP and is now a professor at IHEP. And he has extensive experience with diabae, also EXO and NEXO, and of course the upcoming experiment Juno. And he's going to give us an overview of all the neutrino experiments. So go ahead, I'll give you a warning at 25 minutes.
Okay, thank you. Can you hear me okay?
Yes.
Okay, thanks very much for the introduction. And also thanks for the opportunity for me to do this experimental overview. So now we know the neutrino have masses, but the absolute mass is still a fundamental problem in neutrino physics. So here is the mass spectra of the quarks and the leptons. And the lower limits of these two neutrino masses are set by the oscillation experiments. But however, the lightest neutrino mass is still unknown. In the quark sector, we see this hierarchical structure in the masses and also in the mixing matrix. But in the lepton sector, we didn't see the hierarchical structure, and then we see very different mixing. So this is a very big puzzle. So in the next 10 to 20 years, I think the most important tasks for our experimentalists is to precisely determine the leptonic mixing and determine the mass neutrino absolute masses. And I will try to overview the relevant experiments. So let's take a closer look at the neutrino mass and the flavor mixing. Sorry. Yeah, so this standard parameterization is well known. The 3 mixing angles and 2 mass square difference has been measured. The remaining issues are the neutrino mass ordering and the CP violation phase. For Majorana nature, it can only be probed in neutrino stable decay. I will talk about later. One thing to point out, the mixing angle θ23, if it's 45 degree, we will have this so-called mu tau symmetry. And the octant of θ23 will have impact on the future sensitivity of the future accelerator and atmospheric neutrino experiments. So for mixing angle θ13, it can be measured by the disappearance of reactor electron antineutrino. Diabae, double show, and Reno all reuse the relative measurements, and Diabae has the optimal baseline and a much smaller detector uncertainty and background uncertainty, so it dominates the global precision. And the Diabae has stopped data taking in end of 2020. Using the dataset till 2017, the precision to θ13 reached 3.4%. and 2.8% for datum square. The projected final precision for θ13 and datum square is much lower than 3%. So likely in the next many years, no other experiments will exceed this precision. For θ12 and datum square 2.1, historically known as solar parameters, they can be measured by nu E disappearance from solar and nu E bar disappearance from reactor. In the solar sector, we use 2 features. So one is this precision measurement of the vacuum to matter transition region, and then the other is to measure the day-night asymmetry due to the Earth's matter effects. In the reactor sector, the cabinet experiment has not update their results since 2013 because many of the reactors has been off. And last year, the SuperK has updated its measurements of the solar neutrino ANSYS. The combination of SuperK and SNOW disfavors the cabinet the best fit value at 1.4 sigma. So the 2 sigma, the previous 2 sigma tension was largely gone. For θ23 and the datum square 2.3, This is known as the atmospheric parameters. Now can be also measured using accelerator with better precision. So in the past 2 years, both Super K, T2K, and NOVA all update the measurements. The Super K data now prefers the first octant. The contours for the theta-23 has significantly improved. For T2K, 2 results has been released last year, which is run 1 to run 9 dataset. The best fit theta-23 for neutrinos and antineutrinos are consistent within 1 sigma. After adding run 10 data and using new analysis techniques, the best fit value moved to upper octant. And both these 2 analyses prefers normal ordering. For NOVA data, it also slightly prefers the upper octant, and the theta-23 measurement is very consistent with the T2K results. So now we see the small tension between atmospheric data and accelerator data. For CP phase, now we see clear tension between the T2K and NOVA's preferred regions. As just mentioned, both T2K and NOVA data prefers the normal ordering, as you can see from these blue curves. But for CP violation, the T2K data favors the minus half pi here. For NOVA data, it prefers the 0.8 pi, which you can see here. So compared in these 2 plots, we clearly observe a 2 to 3 sigma tension on the CP phase. So now these 2 collaborations are working together to do a joint analysis to solve this tension. Now back to this plot, let's discuss a little bit about the future. So on the roadmap to solve the neutrino absolute mass, many great experiments have been involved. So my personal view on this, I consider the solution in a stepwise way. So first, the oscillation experiments can determine the neutrino mass ordering so that we know precisely the relative neutrino mass. And then the double beta decay experiments determine the Majorana nature of neutrinos and measure the effective neutrino mass. So if the neutrinos are Dirac, then the only way to measure the lightest neutrino mass is the beta decay or cosmological observations. So let's first see the future oscillation experiments. So their primary goal is to determine neutrino mass ordering and the CP violation. For neutrino mass ordering itself, it's a fundamental property of the neutrinos. The different ordering implies different flavor structure, so it can be a model discriminator. Now we have complementary ways to determine neutrino mass ordering. So reactor neutrino experiments like Juno can give a clean measurement utilizing the interference of these 2 oscillations. As for the atmospheric neutrino and the accelerator experiments, the Earth's matter effect dominates their intrinsic sensitivity. But in addition, both of them can also extract the vacuum oscillation parameters. Approximately referred as this delta square mu mu. And this parameter is different from the delta square EE from the reactor channel. So the difference will bring additional sensitivity to the neutrino mass ordering. For CP phase, we know that it's critical to understand the matter-antimatter asymmetry. So our current strategy is to compare the neutrino oscillation and the anti-neutrino oscillation using using accelerators. So Juno, the Juno experiment is under construction. It will build the world's largest liquid scintillator detector, 20 kiloton, with the unprecedented energy resolution. It will precisely measure the reactor neutrino spectrum. Sorry, let me use a pointer. Sorry about this. It will precisely measure the oscillation spectrum using reactors 53 kilometers away to determine neutrino mass ordering and precision measurement. A satellite experiment, the Juno Tau, is also under design and construction to be deployed near Taishan reactor. So it will provide an independent and precise reactor neutrino spectrum for Juno. Thanks to the large target mass, it can also have rich physics in astro neutrinos and Leucan decay searches. In 6 years, Juno will observe 100K events, and with the excellent energy resolution, the small energy scale uncertainty, and low background, it can precisely measure the amplitude and frequency of these two oscillations and use that to get neutrino mass ordering. The sensitivity for 6 years is about 3 sigma. In future, if the other experiments measure the delta square mu mu to 1% and use it as the input, the Juno sensitivity can reach to 4 sigma. So on the precision measurement side, the precision for these 3 parameters can reach to sub% within 6 years. And in a Juno lifetime, it may even improve an order of magnitude compared to the current direct measurement. So this will be very useful to test the unitarity of neutrino mixing. For Dune and Hyper-K, because there will be a dedicated overview talk on the accelerator-based experiments. So here I just highlight the sensitivities of Dune and Hyper-K. So Dune shoot the neutrino and anti-neutrino beam from Fermilab to Stanford. Because the long baseline and the high energy of the neutrino beam, the matter effect is significant. So even within 2 to 3 years, Dune can unambiguously determine the neutrino mass ordering. For CP violation, it can be discovered in about 7 years if the true CP phase is minus half pi, or in 10 years, 50% of different CP values will be discovered. So compared to this, the Hyper-K experiment used the neutrino beam from Tokai to Kamioka. The baseline and the peak energy of the neutrino beam is much smaller, so the matter effect is smaller, cause less sensitivity on the neutrino mass ordering. However, due to the large target mass and optimized neutrino operation mode, it can have even greater sensitivity on the CP violation phase. But one thing you need to point out is that in this study, the uncertainties play an important impact on the CP violation sensitivity. So various near detectors are under design and to reduce the systematics. On the other hand, if the neutrino mass ordering is unknown, for Hyper-K, the beam only sensitivity may decrease for some values of the CP phase. So in this case, because the Hyper-K has large target volume, so in the atmospheric neutrino channel, it can have sensitivity to the neutrino mass ordering because the atmospheric neutrino has higher energy and a larger Earth matter effects. So the combination of this beam and the atmospheric neutrino study will exclude the wrong ordering at about 4 to 6 sigma, depending on different theta 2-3 values. And this study will also compensate the sensitivity of the CP violation phase. For neutrino telescopes, the primary focus, my understanding is that is the high energy astrophysics but at the low energy end, they can also perform very good neutrino oscillation measurements. The IceCube deep core, for the first time, it has the comparable mixing angle and the mass splitting measurement precision to the long baseline accelerators. You can see here. It can also perform a unique measurement to measure the tau new tau appearance normalization to test the unitarity of this neutrino mixing matrix. For another telescope, the ORCA, its sensitivity study shows that with 3 years operation, it has competitive oscillation parameter measurements and possibly 2.5 to 5 sigma determination of neutrino mass ordering in 3 years. I have to point out that some recent studies show that for both IceCube Gen 2 and the ORCA, the combination with Juno results can significantly increase the mass ordering sensitivity. So let's move to the different topic. The neutrino oscillation experiments can only determine the relative neutrino mass. So to access the absolute neutrino mass scale, we have 3 other probes. So the tritium beta decay, the neutrinonist beta decay, and the cosmological observations. So these 2 types of decays measure the 2 different effective neutrino mass, and this is their current limit. For cosmological observations, they measure the summation of all the 3 neutrino masses. Even though the limit is current limit is seems good, but it still has a large uncertainty. So now let's discuss a little bit all these experiments. So tritium beta decay. So the cartoon is a very beautiful experiment. It measured the super allowed beta decay, and if the different size of the neutrino mass will affect the spectrum shape near the beta decay endpoint. This measurement is very challenging. It requires extremely good energy resolution and systematic control. In 2019, Katrin operated a 4 weeks science run, and the fit result is here. The neutrino mass square information can be extracted from this tail, and it gives an upper limit of 1.1 electron volt at a 90% confidence level. So if you scale the exposure from this 4 weeks to 5 years, you will realize the result is coincide with the target sensitivity. So which means their technology is basically approved. So down the road, so this plot show you the 30 years history of this beta decay measurement. And obviously, Katrin will continue to deliver the world-leading sensitivity until its final goal, the 0.2 EV sensitivity. But unfortunately, this technology, the existing technology, cannot scale up. And there's irreducible systematics associated with the molecular final states at this 100 milli-electron volt. In this case, the project 8, conceived as the next generation experiment to the masses allowed under this inverted ordering range. It requires low technology. It's shown in this plot. The electrons from tritium decay has cyclotron motion in the magnetic field, and it produced the radiation. And this radiation can be captured by the antennas to measure the electron energy. So in this case, it may achieve the 40 milli-electron volt, but certainly this put a stringent requirement on technologies like the sufficient exposure and even better resolution and some atomic tritium source. Let's move to neutrino needs stability decay. A little bit of background. So determining the Dirac or Majorana nature of massive neutrinos is one of the most challenging problems in elementary particle physics. In 1980s, Valley and proved that if double decay happens, neutrinos near stability decay happens, there must be an effective Majorana mass term there, which means the neutrino is Majorana nature. So the double decay experiment offers the most sensitive and the only feasible probe to determine the Majorana nature of neutrinos. It's not only discover a new type of elementary particles, but also process with lepton number violation and to constrain the Majorana physics. So the current limit is here. The best world best limit is here at the around 10 to 26 years. The future goal is to have almost 2 orders magnitude improvement in this half-life to cover the inverted mass ordering region. So all this, in particular, this Nexo and Legend experiments are aiming at 10 to 28 years. And Nexo is a 5-ton liquid xenon TPC, and the Legend is a ton-scale germanium detector in a phase from Gerda to Legend 200 to Legend 1 ton. So suppose that those experiments didn't discover the events. What will it be? So what will happen if we go down to this deep? So recently, there's a study to investigate the allowed parameter space in this double decay experiment. If the sensitivity of the double decay experiment achieves 1 milli-electron volt or even lower, the shape, the parameter space is in this bullet shape, and the allowed region is actually very small. So this means that if we really can achieve this sensitivity, we can precisely determine the lightest neutrino mass shown here. It's better precision than any other experiments. And even though we can, and furthermore, we can further constrain the Majorana phases to a very small parameter space. So this is very attractive, kind of the target for future experiments. So let's see what's the driven factors for the neutrino stability decay. For a long background-free experiment, I just simply use this counting approach shown here. If I reformulate the formula into this equation and redefine the detector exposure and the background index, and draw the existing experiments and the future experiments, we see the clear 2 generations. And we see that in the future, if we want to increase the sensitivity, the background level is certainly a driven factor, one driven factor, but not enough. We need a sufficient target mass. So we should go in this upper left direction. So with this idea behind, we consider the further future of Juno. So Juno, the primary goals is to determine mass ordering and the precision measurement. So after the completion of this primary physics goals, this detector can be upgraded by loading the neutrino stability isotope into liquid cylinder. And thanks to the large volume, it can hold 100 tons of targets. It already, because it's an existing detector, so it provides the best liquid cylinder shielding very good energy resolution and low background level. So if you compare the other experiments, in the future, if we successfully load hundreds tons targets, we may achieve a sensitivity level to milli-electron volts. Certainly, this requires a lot of background control and a new type of liquid designator. It has technical challenges.
So Liangjian, there's about 5 minutes left.
Thanks. So let's move to the another experiment, another way to probe the neutrino mass. So we know that in the early universe, when the temperature of neutrinos is 1 MeV, well, start from high temperature to as low as 1 MeV, the neutrinos start to decouple from the thermal bath and form a neutrino background in the universe. Is the so-called the radical neutrino background. And today, the radical neutrinos have very low temperature and they are long relativistic. So in this case, Weinberger proposed a new idea to detect this kind of neutrinos by using the capture channel on the beta decay nuclei. So this is the signal, and this is the beta decay background. So this is kind of one stone, two birds experiment. It can detect the cosmic neutrino background and also constrain the neutrino mass. And this is the ambitious goal of the Ptolemy experiment. You can see that it requires the high energy resolution to distinguish the different ordering and also the different shape of the spectrum. And with 1 gram per year, 1 gram a year exposure, it can have a good sensitivity on lightest neutrino mass. But this experiment is very difficult. It has a lot of technical challenges. So we are looking forward to seeing the new results soon. So I have 2 more slides because this year is the 20 years anniversary of the solar neutrino oscillation discovery. So I talk a little bit about the solar neutrinos. You will hear more about this in Professor Art McDonald's talk. After the discovery of snow, Bergsino has pushed the extreme on these solar neutrino studies. It discovered the beryllium-7, PEP, PP, and CO neutrinos source, and its data allows to probe the vacuum to matter transition in this plot. And also on the solar neutrino side, the current Z12 precision is dominated by the solar data. So that's the status before this year. So how about after? So in the future, large neutrino detector can all do some study on the solar neutrinos. For example, the Juno has the 20 kiloton liquid designator, so it can have a low energy threshold and low background to study the boron-8 and beryllium-7 neutrino spectrum. The day-night symmetry effect may reach 0.9% uncertainty, and test the upturn effect can reach to 2 sigma. It can also simultaneously measure the solar neutrino and the reactor neutrino to test the oscillation parameters. Very interestingly, it can measure, also use the CC and NC channels here to measure the total flux, which is similar to what Snow did in 2000. And for Hyper-K, it has large statistics, but the energy threshold is higher. But even though they can probe the HEP neutrinos, for Dune, the sensitivity on solar neutrino is less because they have the challenges to deal with the radioactivity and the cosmogenic background. So in future, we will see more results from those experiments. So here is the summary and the outlook. Our neutrino field has entered the precision era by those oscillation experiments. And the mass ordering and their CP is the primary goal in the next 10 years. Hopefully they can be resolved. For mass ordering, it can be sooner. Then this will allow us to deep understanding the leptonic flavor structure. The ultimate goal of neutrino physics is to understand the origin of the universe, origin of neutrino masses. Let's keep eyes on the double decay. Sorry, due to the limited time, many other important fields and experiments are not be able to cover in my talk. Okay, thanks very much.
Thank you very much, Liangjian. That was a very comprehensive review of a very extensive experimental program. So we have many questions in the chat. We'll get to a few of them here, but the rest will move to Slack, and I encourage you to discuss things there. So the first one is from Gustavo Alves, who is asking about CP violating effects due to the matter effect and CP violation due to the delta phase, and how these are differentiated at experiments.
Delta phase. Sorry, can you repeat the question?
So I think this person is asking about, so there's a CP violation from the complex phase, right? And there's CP violation from matter effects. And how experiments get a handle on these two and how they can tell the difference.
I see. Okay, so probably I need to pour out the oscillation formula in this long baseline experiments. It's a very complicated. The CP and the matter effects are hidden in the oscillation spectrum for these two experiments. To be honest, I don't know the exact detail of these experiments, how to decouple the CP and mass ordering effects. But I can look into it and give a more precise answer in a Slack.
Okay, thanks. So another one, this one's from Maxim Dvornikov, who asks, if a supernova explodes in our galaxy, how many events will Juno see?
Okay. So in our yellow book, suppose there's a 10 kpc supernova, we may observe 5,000 inverse beta decay and a few hundreds of electron scattering. And also, if we can have a low energy threshold, we can also observe thousands, maybe 2,000 of scattering on protons.
Okay, sounds good. The final one we're going to do here is from Hariam, who asks about how we detect neutrinoless double beta decay. Because the cross-section is very small for neutrino interactions, one can wrongly think the neutrino did not interact in the detector.
For the detection of neutrinoless double decay?
Yeah.
Okay.
You had the plot from Weinberg, which might be nice to look at.
This one?
This works too, yeah.
Yeah, so for experiments, I think it's very simple. We measure the summed energy of these betas. If it's Majorana, then if neutrinos are Majorana neutrinos, we will see a peak of the total energy at a Q value. But if neutrino are not Majorana particles, this process cannot happen. So we cannot see the peak. So basically this kind of experiment is to look for the the peak signature in the energy spectrum. It's very straightforward.